Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on January 2nd, 2026, about 6 days ago. It introduces a hierarchical learning framework for massive 6,000 kilogram robots that achieve centimeter-level accuracy on unstable terrain by merging high-level reinforcement learning with robust low-level control. The paper is titled, Vision-Based Goal-Reaching Control for Mobile Robots Using a Hierarchical Learning Framework. And as we'll see later, the real-world results on soft soil are quite impressive. Alright, let's break down the planning layer. Figure 1 details the architecture of the Reinforcement Learning Motion Planner, which operates at a kinematic level. It starts with the state feature extraction block on the left, where the robot's current distance and heading errors are processed. These features feed into the central learning loop, outlined in purple, where the policy uses an epsilon-greedy strategy to choose actions. Crucially, this loop also computes rewards, balancing task completion with shaping terms to ensure smooth, efficient learning. Okay, moving down the hierarchy, Figure 2 illustrates the training pipeline for the inverse dynamics model. The left panel highlights the data collection from the robot's complex in-wheel actuator system, which includes hydraulic motors and gearboxes. This real-world data feeds into the deep neural network on the right, which acts as the inverse dynamic model. By minimizing the mean squared error during the training loop, the network learns to accurately predict the control inputs needed to execute the planner's smooth commands. So, Figure 3 assembles these pieces into the complete, real-time framework. On the right, the Orbi-SLAM 3 system continuously tracks the robot, feeding pose estimates into the trained reinforcement learning model on the left. This planner sends safe motion references up to the control layer at the top, where the deep neural network and an adaptive feedback regulator work together to drive the wheels. Finally, the safety supervisor at the bottom monitors the entire operation, ready to take over if the robot exits the safety zone visible in the center. Having outlined the system, Table 1 specifies the exact constraints and parameters used to train the Q-learning policy. The top rows define the simulation environment, showing that the model trains for 30,000 episodes with a fine time step to ensure robust convergence. Moving to the middle section, we see the strict kinematic limits required for the 6,000 kilogram robot, such as a maximum linear speed of just 0.25 meters per second. Finally, the bottom rows detail the learning dynamics, including a discount factor of 0.95 and a decaying exploration rate. Well, having defined the parameters, Figure 5 demonstrates the system's safety logic in action during real-world experiments. The left panel maps the trajectory on asphalt terrain, where the robot successfully navigates between multiple waypoints shown in yellow. Once a simulated safety violation occurs at the top, indicated by the red marker, the safety supervisor immediately triggers. It overrides the planner and autonomously guides the robot back to the green safe inspection area along the red path. The right panel confirms that this fail-safe mechanism works just as reliably on rough, loose soil terrain, ensuring the robot can recover even in difficult conditions. Alright, while the previous figures showed the paths visually, Table 5 quantifies exactly how well the controller performs compared to other state-of-the-art methods. The top row highlights the proposed deep neural network-based robust adaptive control. It achieves a peak time of 4.1 seconds and a remarkably low steady-state error of just 0.009 meters per second. In contrast, the standard backstepping and model-based approaches in the bottom rows suffer from higher overshoot and larger errors, confirming that the proposed method offers superior tracking precision. Wrapping up, this work proves that safe reinforcement learning is viable for massive 6,000 kilogram robots on unstable terrain. By separating planning from robust control, the framework achieves centimeter-level precision without risking safety. This paves the way for autonomous heavy machinery in harsh environments. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.